Hello, y'all. Welcome to lesson 104 of my DP chemistry curriculum. This is reactivity 3.1.14 and 15. In 14, we're going to talk about how acid-base indicators are weak acids, where the components of the conjugate acid-base pair have different colors. The pH of the endpoint of an indicator, where it changes color, is approximately correspondent to its pKa value. We'll talk about how and why we know this and derive that as well. We'll be able to construct equilibria equations to show why the color of an indicator changes with pH. In 15, we're going to talk about how we choose an appropriate indicator for a titration, where the endpoint range coincides with the pH at the equivalence point. So we're going to see that endpoint and equivalence point are different things, but we need both. We'll be able to identify an appropriate indicator for titration from the identity of the salt and pH range of the indicator. So it seems like quite a lot, but this is actually a pretty short lesson. So let's talk about what we're starting with, which is indicators are actually just weak acids. They can sometimes be weak bases, but weak acids or bases in which the dissociated and undissociated forms have different colors. So basically, if we were to look at this as a chemical equation, we have H indicator, H representing that this is acidic and an aqueous solution, reacts and or dissociates in solution to form H plus ions, aqueous, and the remaining indicator conjugate base. So it's a weak acid and a weak conjugate base in solution. So these exist as we see from the double arrow, they are in equilibrium. I'm going to use EQM. Therefore, the addition of acid or base, and when we're discussing Bronsted Lowry acid bases, we're talking about donating or accepting hydrogens, but we can also think about it in terms of H plus or OH minus respectively. So by adding this, we'll shift the equilibrium. Therefore, changes color. So when we look at our indicator, one thing of note is that we would likely have one color for our undissociated form and a different color for our dissociated form. So you might say this is color A, while over here we have color B. And so by shifting that equilibrium, we are shifting the color. You can even have both colors happening at once, which would give you that gradient range. So basically, when we're looking at indicators, one of the things we have to constantly keep focus of is Le Chatelier's principle. Because as we look at Le Chatelier's principle, we notice that an acid or H plus will shift towards the left or the undissociated side. So as we add our hydrogen, we'll shift back towards our original side. Meanwhile, if we add a base, OH minus, that would remove the hydrogen and shift right towards, or shift towards right. Just rearrange those. Which is our dissociated side. So using Le Chatelier's principle, as we remove hydrogen, we will continue to produce more of our dissociated form to add hydrogen back. We're trying to resist the change. That is what Le Chatelier's told us. If we look at the equilibrium constant of the acid that is the indicator, Ka, using that equation, we see that H plus our indicator will be divided by H indicator. Using this equilibrium constant, we notice that if our concentration of our indicator is equal to our concentration of the conjugate is equal to the concentration of the indicator, in our equation we could cancel these out. We see that that is actually where the Ka equals the concentration of H plus. This is therefore where the color shifts. Color changes. We can also then take this and extrapolate further that if the Ka equal to H plus, then the pKa is equal to the pH of the indicator when it changes. So we know that our indicators change when their pKa equals their pH because our concentration of the indicator in its conjugate form and the indicator in its standard dissociated form are equivalent, which kind of makes sense if you look back at the equation. If we have equal amounts of, whoops, if we have equal amounts of this and this, then we're right in the middle point between our two colors. So our color shifts as we move more towards one or more towards the other. But at the equivalence point, our Ka will equal our H plus and our pKa will equal our pH. And that is that color change point. So taking this a little further, let's start defining a couple of these terms. So we know that these are weak acids that change color over a range. So usually it's not one exact point because as you start decreasing the amount of one form, you'll increase the other form, but you still won't be all the way to your color A or all the way to your color B. You get that gradient. So they change color over a full range. Now, within that range, that actual point, the center point, the center of range, that is called the end point. It's different than the equivalence point. The end point is also the specific part where we say there is the color change of the indicator. Many indicators have a gradient, but some have a smaller gradient than others. You might notice with things like phenolphthalein, which we use in titrations often, it is a very sharp contrast, but you do get a light pink somewhere in the middle. It's not always the clear or the very dark pink. You sometimes get that light pink, which tells you you're at the end of your titration. However, the big clarification is that the end point does not equal the equivalence point. Equivalence point. The equivalence point is in your titration when your volumes of acid and base are the same or your moles of acid and base are the same. The end point is specific to each individual indicator, and it is when your H plus, or sorry, your indicator concentration and indicator conjugate base concentration are equivalent. Now, this is very important because we use indicators in titrations. And so in a titration, a proper indicator is chosen where the endpoint coincides or aligns with the equivalence point. So we're going to take a while to look at a couple examples, and that will be about it. So I have a couple images of various titrations. Uh, we'll go with that one. And we'll move this one further down. So in this image of a titration between what we can recognize as a strong acid and a strong base, we can see our strong base is our analyte. Our pH is starting very high. We also know that our pH ends very low. So this is our strong base, and we are titrating in a strong acid. Our equivalence point, the center of that, is at 7.0. So we know it's strong and strong or weak and weak, not strong and weak together. Furthermore, we can look at our indicator being chosen. So for this one, we're choosing bromothymol blue. It is blue very high, it is yellow very low, and we get our gradient where we get a little bit of green right around the equivalence point. Its range is 7.6 to 6.0. So our equivalence point is right in that section. Bromothymol blue is a good indicator for this reaction, and we can tell because it will change colors across the equivalence point of our titration. When we look at phenolphthalein, which is one of our most common indicators, we can start determining whether or not it is actually the best indicator for a reaction. You'll notice that its endpoint is actually not very well aligned with the equivalence point of our reactions, yet we continue to use it. So while phenolphthalein is not the best, it is actually okay, turns out. You'll notice that the full colorless range is below the equivalence point, while any color whatsoever is above the equivalence point. So this is generally why we tell you to stop the moment you can see any sort of pink color forming as you're titrating, or the moment it goes completely clearless. You're all colorless. You'll notice this is usually why we also start with our acid. We go from colorless into our colored form. It's an easier transition to notice than the other way around. For strong acid, strong base titrations, we actually are a lot more forgiving with our indicators of choice because this change happens so fast and covers such a large range of pH values that most indicators will work for a strong acid, strong base titration. The last option I'm going to show you is where we see two different indicators as a possible choice. We can recognize this as a strong base and a weak acid. Our equivalence point is within the range of phenolphthalein, so our phenolphthalein will tell us when it's basic or when it's acidic. However, you'll notice a different indicator, methyl orange, is a bad indicator for this. Its entire color change, its entire endpoint, does not even reach the range of our graph or the range of our titration. Methyl orange would not be acceptable for this titration. You will notice, however, that if we were doing a strong acid, strong base titration, methyl orange would in fact still work. Strong acid, strong base titrations work with almost any indicator. Some exceptions might be crystal violet, which have an endpoint in the range around 1 or less than 1. But for the most part, any indicator will cover that vast range. So you just have to make sure that you're usually choosing one that will have an endpoint near the equivalence point. So just some good ways to figure out the proper indicator. First thing you need to do, so choose an indicator. The first thing you need to do is determine your acids and bases. You want to know what you're dealing with. Second, you want to get the pH of equivalence point. Once you know the pH of your equivalence point, and you can usually estimate it because you know strong and strong, so strong acid, strong base will generally be 7. Weak acid, weak base will be 7. Strong acid, weak base will generally be in the range of 3 to 5. And weak acid, strong base will generally be in the range of like 9 to 11. So your pH of your equivalence point will vary, but you generally have an idea of the range. And then finally, you choose an indicator where endpoint, so that's the indicator value, is approximately the equivalence point. So that's it for indicators. I hope this lesson helped you understand them a little bit better and helped you figure out which indicator to choose. Have a great